The surprising truth about self-healing materials is that the hard part is not healing. The hard part is proving every time that the structure is truly safe again. By 2026, the science is no longer a single trick. Peer-reviewed work maps out many different healing pathways across polymer composites, fiber-reinforced polymer laminates, thermoplastic-containing structural composites, and even concrete-based systems. Some rely on reversible chemistry, where bonds break and reform. Others use supra-molecular interactions, more like molecular Velcro. Some embed capsules that release a healing agent when a crack forms. Another family uses vascular channels, like tiny plumbing, to deliver repair material where it is needed. Concrete systems lean on crack closure and self-curing behavior, often tied to moisture and cement chemistry. There are also designs where exposure to air or water helps trigger repair. Yet maturity is uneven. Many demonstrations look great on small test samples under controlled conditions. Moving from that to a safety-critical wing, blade, bridge, or pressure hull is a different world. The biggest gaps are repeatability, modeling, non-destructive verification, and standards. There is still no shared acceptance threshold for healing efficiency, residual strength, fatigue life extension, crack width range, or how many cycles of damage and healing you can count on. That last point matters. A one-time healing event is not the same as a lifetime capability. Some approaches are intrinsic, meaning the material heals by rearranging its own chemistry. Those can, in principle, repeat. Other approaches are extrinsic, like capsules or reservoirs. They can work well, but they can also deplete. And even intrinsic systems can age or lose performance under heat, ultraviolet exposure, moisture, or chemicals. For capital allocators, the real question is not, can it heal once? It is, under what conditions, for how long, and how do we know? Damage mode is the next reality check. Many mechanisms can plausibly address polymer matrix micro-cracking, where the matrix develops tiny cracks that reduce stiffness and invite moisture. In contrast, fiber breakage is a hard physical limit. If load-bearing fibers are severed, matrix healing alone cannot fully restore the original load path. Delamination and interface damage are also tough, because the laminate architecture may not be recoverable with a simple resin fix. In concrete, the story shifts again. The central value may be reduced permeability and slower corrosion, not a clean return of mechanical strength. Crack width, moisture availability, and exposure history become decisive. Because of these limits, the most important shift is architectural. The field is moving from the material heals to the structure runs a loop. First, it senses damage. Then it triggers a repair process. Then it verifies recovery. Finally, it updates maintenance state, like a living asset ledger. That full loop is what responsive structural systems are aiming for. Verification is the gatekeeper. Self-sensing smart polymer composites are already treated as coupled systems, where sensing and healing are designed together. But it creates a new kind of risk. False negatives are dangerous because they can leave hidden damage in service. False positives are expensive because they can force unnecessary derating or replacement. For regulated industries, the question becomes whether self-sensing can ever be trusted as a verification channel, not just a diagnostic hint. Modeling sits underneath all of this. The field needs ways to connect healing kinetics, transport of healants, crack geometry, and the structural load path. That means linking mechanism scale models to macroscopic metrics like stiffness, fracture toughness, fatigue life, and permeability. It also means propagating uncertainty, because certification is about confidence, not just averages. Manufacturing is another constraint that does not show up in glossy demos. Capsules, channels, and thermoplastic phases can change baseline mechanical performance. A healing architecture that weakens the original laminate may be a net loss, even if it heals later. So the manufacturing route has to embed the mechanism without undermining the structure you are trying to protect. One peer-reviewed example from 2020 is especially telling as a design motif. Elytra-mimetic-aligned composites were reported with air-water responsive self-healing and even self-growing behavior. The takeaway is not that buildings will grow next decade. The takeaway is that environment-triggered response is real, and it can be engineered into structural materials, but only within strict limits. So what should a senior decision-maker do with all this? Treat self-healing as a claim that must be operationalized. Require the mechanism class, the target damage mode, the residual property recovered, the recovery percentage, the cycle count, the time to heal, the environmental conditions, and the verification method. Without that, self-healing is marketing, not asset performance. Fund staged demonstrators, not broad deployment. Start with coupons and subcomponents.